Hello folks, welcome to the Age of Asparagus and the fourth part of phase 2 of making a 3D top-down shooter in Godot. By the end of this video, our level generator will place objects in such a way so that the center tile will always be open for our player to spawn in, and we'll use a flood fill algorithm to prevent objects from cutting off any part of our level so that all open spaces remain connected. Okay, the first thing we want to do, if I hit 7 here to go into top-down view, is I want to make sure that the center of our map never has an obstacle there, because that's where we want to spawn our player. So if I click on the map and just change the seed here, you can see that our obstacles can be generated there. That should be pretty easy. So let's go to our map script, and at the very top of our script here we're going to create a new variable and we'll call it map center, and we want this to be a coord object, our custom inner coordinate class with an x and a z value, and we're going to set the map center anytime that we change the width or the depth of our level. So let's go to the width and depth setters, and underneath that we'll create a new function and we'll call it update map center center, and we can say map center equals coord.new, and we'll set it equal to the map width divided by 2, and the z value will be the map depth divided by 2. And we're going to want to call this method before we generate our map after we update the width or the depth. Okay? And then the last thing we're going to need to do is down in our add obstacles method, right before we add the obstacle, let's just check and make sure that the coordinate where we're trying to make the obstacle is not the map center. So let's go if coord does not equal map center, then we can create an obstacle here. Now, this isn't actually going to work. If we change seeds, we're still going to get obstacles appearing in the center, and that's because, oops, let's save that and give it a try. We're still going to get obstacles at the center, and that's because GDScript doesn't know how to compare two coordinate objects. That's a custom class we created, so these are objects, and these are not the same object, so they're not going to be equal. And unfortunately, we can't override operators in GDScript. At least that did not appear to be the case from my scouring of the documentation. However, we can just create our own little equal method. So let's do that up here in our coord class. Let's just go func, and we'll call it equals. Good enough, right? And then we're going to pass it another coord, and then all we'll do is we'll return let's just type it the kind of easy to read way. We'll go if coord.x equals x, and this, you could also put self.x here if you just wanted to be clear, and coord.z equals self.z, then return true. And we could have else return false, but just an easier way here is we're just going to return that. So if the coordinate that we're providing, the equals method, has the same x value and the same z value, it'll be true. Okay? Does that work? Let's get rid of that. It's no longer an if statement. Good. So now when we go down, we can compare two coordinates. Here, we can go if coord dot equal. Now, because this is in a loop here, in an iterator, we can't provide type hints for this. So instead, let's use the map, just to make sure we're doing it right. Let's use map center dot equals, and then we can pass it the coord. And then we want to say if not, right? Because if they're not equal, then we can create an obstacle. Let's try that. Go up to 3D view here, and it's promising so far, but let's just try a few seeds and then make sure we don't get anything appearing there, and that looks pretty confident. And of course, if we turn our obstacle density up to max, we should get everywhere except for the center. A little bit of lag there. Okay, now the next thing we want to do is we want to make sure that our level doesn't generate these little pockets. If our player is spawning here and an enemy spawns here or here, the enemy isn't going to be able to find a path to our player. And the player will be stuck, and this will be a pretty dumb game. So as we're placing obstacles, we want to make sure that no sections get cut off, not even little single ones where enemies could possibly spawn and just get stuck and unable to leave. And we're going to do that with a flood fill algorithm, which if we go here and we reduce the obstacle density a little bit to something like this, and actually, you know what, let's reduce this right down to a width of 5 and a depth of 3, something really simple here. And I'm going to go to seed 12417, and I'm hoping you will get the same result if you enter that seed as well. And I'm going to have an obstacle density of 0.3. Okay, so as we're placing obstacles, we need a way to determine whether placing a new obstacle, let's say we've placed these 3 and everything's good, and then now we're going to try and place this obstacle, and we want to determine whether it cuts off a section of the map. And what we're going to do is we're going to start at the center of the map, since we know that one's going to be open, and we're going to use a flood fill algorithm. And you can imagine if this was a paint program and you dropped your paint tool right there, you can imagine that all of this would fill up with paint. And then what we're going to do is we're going to compare how many coordinates, how many of these cells ended up getting filled with paint compared to how many we should expect to fill up with paint. If everything was open, then these would fill up with paint too, and we could go, oh yeah, the number that filled up with paint equals the number that we expected to. However, in a case like this, we'll go, wait a second, we only got 7 squares filled up with paint, whereas we were expecting 11. And then we'll know, well, this object cannot go there, we'll remove it, and then we'll try another place. So algorithms are pretty fun, but when you just go dive right in and write them in code, especially for people who've never seen them before, it can be pretty confusing. So I'm going to explain as best I can how the flood fill algorithm is going to work in the way we're going to implement it. Okay, so let's say this is our level, and so far our level generating tool has placed 3 obstacles at 2, 0, 3, 0, and 3, 1. And the next obstacle it tries to place is at 2, 2. Now we're going to run our flood fill algorithm to make sure that the map is still fully connected. And obviously it isn't here. You can see these 4 squares have been cut off. But let's walk through the process to see how that's going to work. So I'm going to run through some of the data and variables we'll need to complete our algorithm here. We'll need an obstacle map variable to hold the position of all the obstacles in the level. That looks something like this. Since the obstacle map is a 2-dimensional array where this would be 0, 0, this would be 0, 1, and this would be 0, 2. So we're talking about this spot, and this spot. And then the next element in the array would be the next column. So to make this a little easier for us, I'm going to display this a little differently. I'm going to display that same array like this, so visually you can see that it matches whether there's an obstacle in these 3 cells in this column. So false, 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 and then you can see how we get our full map. And if we add the array indices, you can see this maps nicely to our x and our z coordinates, and it becomes really easy to see how these true values map to the location of our obstacles in our level. So as we conduct our algorithm, we are going to need to track which cells we've already checked over. So we're going to do the same thing. We're going to create a 2-dimensional array of Boolean values that will be true if we've already checked that cell. And there it is. We'll initiate them all to false because we haven't checked anywhere. We're also going to create another array, coords to check, and that'll be our queue for which cells we need to look at next. And to initialize this process, we'll throw in the starting cell, the very center, 2, 1, into our array, and that's all it will contain at this point. And finally, we'll create another variable that'll hold the current coordinate that we are checking. As part of our initialization, we should probably also set the fact that we've already checked the center tile 2, 1, and so we can set that to true. And what that means is we've already considered it, we maybe have already put it in the queue. Maybe a better name for already checked would be already queued or something, but I'm going to use already checked, not to be confused with the fact that we still actually need to run the algorithm over it. Okay, so I'm going to write a little bit of pseudocode here that's just going to outline our algorithm, and then we'll walk through it and see how it works. So we're going to start with a loop that checks whether there are any coordinates left to check. We're going to be pushing and popping coordinates in and out of our coords to check array. And as long as there's something in here, the loop is going to continue. So we'll pop the coordinate. We're going to loop through its neighbors. And then as we loop through each of its neighbors, we're going to make sure we don't go off one of the edges. We're also going to make sure we haven't checked here yet. We're going to make sure it's not an obstacle. And if all those things are true, then we're going to add it to our coords to check array. And then finally, we'll mark that coordinate as already checked. So I'm sorry about the confusing terminology here, the way I named them, but we're going to mark it as checked, which means we'll mark it true in this array when we add it to our queue of which ones we want to check over. Really, this should say already added to the coords to check. Maybe would be better, but. And I'm just going to change the coloring here to coordinates that are already checked. In an actual flood fill algorithm, this might be the point where this pixel gets filled up with the color you're filling it in an actual like paint program, for example. So I'm just going to change this over to cyan to differentiate the colors, make it a little easier to follow. Okay, so let's go through this. Let's try it. We'll start at step 1 here. While there are any coordinates to check, yes, we still have one, so let's go into this loop. We'll pop a coordinate. Let's pop out the only value in the array, and we'll assign it to our current coord variable, and let's loop through the neighbors. Now we're only worried about the neighbors that share a full edge. We're not worried about diagonal neighbors here, because enemies won't be able to pass through that corner, and similarly in a flood fill, depending on the algorithm, the color might or might not leak through a corner like that. So let's start with this neighbor. The order of the actual neighbors will depend on how you implement that loop in code, but we'll start with this one, coordinate 1, 1. Does it go off the edge? Nope. Have we checked here yet? Well, we can see we haven't, but let's check in our already checked. We got false, so we have not checked. And is it an obstacle? Obviously it's not, but we will be checking our obstacle map. 1, 1 is also false. So we'll add it to our coordinates to check, 1, 1, and we'll also mark it as checked. So at 1, 1, this will become true, which is like painting that pixel with the color. Now we're still in this loop here, so we'll go to the next neighbor and go through the same process. So we're not going off an edge. We haven't checked here yet. This is 2, 0, and it's not an obstacle, 2, 0, actually. It is an obstacle, so we're done with that one, and we'll move on to the next one. You can see what's going to happen. It's an obstacle, so we'll skip that one. It's an obstacle, so we're going to skip that one. Now we're done looping through the neighbors. We end up back on our outer loop to check again if there are any more coordinates. There's a new one, so let's pop it, and we'll start looping through its neighbors. So we'll have these 4. Let's start with this one again. Doesn't go off an edge. We haven't checked here yet. It's not an obstacle, so let's add it to our coordinates to check. This is 0, 1, and let's mark it as checked. Moving on to the next neighbor, we don't go off an edge, we haven't checked here yet, and it's not an obstacle, so we're going to add it, 1, 0, and we'll mark it as checked. The next neighbor here, we don't go off an edge. We have checked here already. As you can see, we're going to check this one right here, 2, 1. We have checked. So let's carry on to the next neighbor. Doesn't go off an edge, haven't checked here. I think you're getting the idea, right? Not an obstacle, so let's add it to our queue, 0.12, and mark it as checked. Okay, so are there any more coordinates to check? There are a bunch of them. So let's go ahead. Let's pop one of the coordinates. We're now looking at 0, 1. So here we have it. We're going to loop through the neighbors. This one goes off the edge, so we're going to ignore that one. This one we haven't checked. It's not an obstacle, so we're going to add it to the queue and mark it as checked. This one we've already checked. This one looks good. Add it to the queue. Looks like we're out of space. And we'll mark it as checked. Should have been flood filling these as we go. These pixels get filled in. Now in our game, obviously, we're not coloring the blocks filling in pixels. We're just marking them in our two-dimensional array that they are open and free and accessible from this point in some way. So I'll just do one more here. Let's pop the next coordinate, 1, 0, and we'll go through its neighbors. We're now on this one. And you can see here, this neighbor's off the edge, this neighbor's an obstacle, this neighbor's already checked, this neighbor's already checked. Nothing to do. Pop the next one, 1, 2. Same thing. Pop the next one, 0, 0. Same thing. Pop the last one, 0, 2. Same thing. So at this point in our loop, while there are coordinates to check, this coordinates to check array will be empty, and our flood fill algorithm will be complete. If we were creating a painting program, all our pixels would now be colored. However, we're not painting. We just want to know if the whole map is accessible. So how do we use everything we've done so far to determine whether the map is accessible? Visually, it's obvious. But how does our code know that? What we're going to do is we're going to compare the number of tiles that should be accessible to the number that actually are accessible. So we'll have a target count, which is just going to equal the total number of cells less the number of obstacles. Which in this case, this is a 5 by 3, the total cells is 15, the number of obstacles is 4. So we'd expect to have 11 tiles accessible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And what we'll do is we'll compare that to the actual count, which is 1, 2, 3, 4, 5, 6, 7. And actually, there's one little extra step in here we're going to want to do, is we're going to want to increment, every time we find an accessible one, we're going to increment a count variable, which will be that one. So every time we mark one of these blue, we'll add 1 to it. We can compare the target count with the count, and if they are the same, we can return true, which means adding this obstacle will keep our map accessible. But in this case, adding this obstacle blocks part of the map because the target count is not the same as the actual count, and the method we'll create will return false. And after we do that, we'll remove this obstacle and we'll try and place it somewhere else, and we'll repeat the process. Okay, let's write this in code. So let's go back up to the top here, and we're going to create a new variable. And let's just do it underneath our map coords array, because this is going to be another array. And we'll call this one our obstacle map. And we'll just set this equal to an empty array. And somewhere down here, we'll need to fill up our obstacle map. So let's do it underneath the fill map coords array method. Create a new function called fill obstacle map. Fill obstacle map. So our obstacle map is going to be a two-dimensional array of Boolean variables, true and false. So let's start by setting the obstacle map equal to an empty list, empty array, obstacle map. And then we're going to loop through the X and the Z values, the width and the map. So now here, since we're creating a two-dimensional array, every time we loop through an X value in the width, we're going to have to append another empty array. This will create our second dimension. So obstacle map dot append, and we'll append an empty list. And then as we loop through in this case, for example, like our 3 Z values in the depth, we will obstacle. Why don't you like my, comma dot append. There we go. Yay, okay. Obstacle map, and we'll take the X in the first dimension, and we'll append we're going to append false, because we're filling it up with Boolean values, where true is an obstacle and false indicates there is no obstacle there. And if you just wanted to check that this is working, of course, you could print the obstacle map. And we scroll down. Of course, we never call fill obstacle map, so we should do that now. And we'll do that at the top of our add obstacles method. So we fill the map coords array, and then we'll fill the obstacle map. And when I save it here, you see, of course, it's going to do it a whole bunch of times. But if I clear that and then just update the seed, you'll see it's a 5 by 3-dimensional array, just like our width and depth. And all those indicate cells with no obstacles. Whew, okay, so let's jump in. We're going to need to create a variable here that's going to hold our current obstacle count. And we'll set that equal to 0. And then what we're going to do is, before we place the obstacle permanently, we're going to make sure that the map is fully accessible. But to do that, we actually need to temporarily create the obstacle. So we'll actually create it, and then we'll also increment our current obstacle count. So we'll go plus equals 1. We'll also set our obstacle map to true at this point. So this is going to be coord.x. Remember, this is two-dimensional array. And then coord.z, and we'll set that value to true. And then once we've registered the obstacle there, in fact, we even created it, which we don't need to do. So let's comment that out. We're going to create it. That could probably be a big performance hit, right? Creating the obstacle, actually creating the obstacle in the scene and then deleting it after if we find out it's bad. Really, our algorithm's only going to use the obstacle map, this Boolean value. So we don't need to actually create the obstacle here. Okay, so now we're going to check if the map is fully accessible. This is the method that we're going to create, that it contains our flood fill algorithm, and that is not close to how you spell accessible. Accessible, maybe? And we're going to send it our current obstacle count so that it can check to make sure it can fill up all the open spots that it's expecting to. And if the map is fully accessible, then we will actually create the obstacle here at xz. Otherwise, we're going to want to remove the obstacle. So what we'll do is we'll take away that count, minus equals 1, and we'll also set that location back to false again, because we never actually did create the obstacle in the scene. Alright, so now the last biggest step here is we need to create our flood fill algorithm. So let's do that right below here. New function, map is fully accessible. And this is our flood fill. Frodo fill. Okay, some variables. We already checked here. And that's going to be, remember, a two-dimensional array of Boolean values as well. So we're going to have to initialize that. Let's go up to our fill obstacle map and do the same thing here. How'd I land? There we go. So we'll go for x in range map width, and this time it's going to go, we already checked here, and we'll set fill up this two-dimensional array with false values. Another variable we're going to need is coords to check, and we'll set that to, that's going to be a list, and we're going to start with only the map center in there. We initialized our we already checked here to false everywhere, but we actually want to set the map center as true. So mapcenter.x and mapcenter.z, we'll set that one equal to true because we have already checked there. And the last thing we're going to need is our accessible tile count, which we will count up every time we check a tile and it's good, it's empty. So we'll set that equal to 1 because we're starting with the map center, which we know is already accessible. So like I explained in the algorithm, here we're going to start our code. So the loop is while we have coords to check. Oopsie, coords to check. And you could check if this is an empty list, but similar to Python, GDScript will, if this is an empty list, it will be a falsy value and it'll break the loop. So we can write it like this, it's much easier to read. We can print things along the way, but I think I'm just going to plow through this since I spent quite a bit of time explaining how the algorithm works. So let's go, we're going to set our current tile equals coords to check, and we're going to pop. What methods do we have? Front or back? It doesn't really matter, so let's just pop from the front. That's going to remove the value. This is now going to be an empty list, and we now stored the map center in the current tile. And now we're going to loop through the neighbors. So we'll go for x in, and I'm just going to put -1, 0, 1 here. And we'll go for z in, again, -1, 0, 1. So these are the offsets from our current position, from the current tile that we want to check. So let's create a new neighbor coordinate. Neighbor equals coord.new, and we'll give it the value of current tile.x. You know what? Let's give this a type hint of coord because I just, I like the autocomplete to save my horrible typing skills. And current tile dot z. It didn't seem to help, did it? Let's not print out. I'm just going to jump up here and not print out our obstacle map. Don't need that. Okay, so we're going to set our neighbor to the current tiles, X and Z, offset by the values in these loops. So we're going to add the X value, which will be -1, then 0, then 1. So we're going to kind of go in a ring around the current tile, plus Z. Let's add some spaces in there. Now, we don't want diagonal neighbors, so if the X value equals 0 or the Z value equals 0, then that means it's going to be a non-diagonal neighbor. Because if it's -1 and -1, it's a corner. If it's a 1, -1, it's a corner. Either the X or Z value has to be 0 for it to be like a horizontal or vertical neighbor. That should have been a comment. And in fact, why don't we move this variable creation into the loop so we're not creating tons of unnecessary variables. Next, we want to make sure we don't go off the map, which I think I'm just going to put into a different method to keep this a little cleaner. So we'll just say if on the map, and then we'll pass it the neighbor coordinate. And we can create that here. Function on the map. Let's get rid of these errors away for now. Okay, so how do we know if we're on the map? Well, let's just return. This will be true. We're on the map if neighbor.x is greater than or equal to 0 and neighbor.x is less than the map width, and neighbor.z is also greater than or equal to 0, and neighbor.z is less than the map depth. I'm going to pull that in and see all the code. Hopefully that makes sense. We'll find out soon enough if it fails, if I screwed up my logic there. So next, we're going to check if we... you know what? These comments are kind of pointless because the way I'm naming my functions is kind of self-documenting, right? So the next one is going to be, so if we haven't already checked there. So if not, we already checked there. In not, it would help if not, we already checked here. And we're going to give it the neighbor.x and neighbor.z. If not, we already checked here. So if we already checked here is false, we haven't checked here, then we can keep going. And if it's not an obstacle, so if not, obstacle map, same thing. Actually, I can probably just copy this whole, this is also a nested list. So there's no obstacle. If we get here, there's no obstacle. We haven't checked here yet. It's on the map, and it's a non-diagonal neighbor. Well, that looks like a hit, right? That means we can fill this with paint, which in our case is just setting, we already checked here to true, except instead of the map center, we're going to set the neighbor's value to true. We're going to add it to the chords to check, which really means the chords that we need to check their neighbors on still. And we'll append the not chords to check, we'll append the neighbor. We're going to increment our accessible tile count. And that is our algorithm loop here. So the only that's going to go through, this is our flood fill. And the only thing we need to do now is after our whole loop is finished, we need to go check that we were able to fill up the target number of cells. So let's create a new variable called target accessible tile count. And that's going to equal our map width times our map depth. So that's all the cells, but then we're just going to subtract the current obstacle count. That will tell us how many cells left should be open if we were able to flood fill the entire map. So that's our target obstacle count. And now we can just check if the target obstacle count, target accessible tile count, sorry, is equal to the actually accessible tile count that we've been counting up as we fill the flood fill the map. Then, good location! And we can return true. Else, bad location cuts off a part of the map. And then we'll return false. So when we return false, let's get rid of some of this extra space here. When we return false, remember up here when we're adding the obstacles, if map what? That should say map is fully accessible. So if the map is fully accessible, if that turns out to be false, we'll subtract that temporary obstacle we placed there, and we'll remove it from the obstacle map, and then the loop will go through to the next possible location for an obstacle, and it will try and place it there. I'm a little nervous. Let's do it. Did it work? We're not getting errors. That's a good sign. It's looking good. I'm not seeing little pieces cut off. Let's go big. Let's go big. Go big or go home. Fill this up. Looks good. Let's crank up the obstacle density here. You see anything getting cut off? Oh, this is pretty neat, isn't it? Let's crank it right up. Yeah, that worked. It worked. So cool. Let's see if we can just make this as big as we can go. Which I think was like 20. Oh, this is going to get a little bit of lag here because we do not have the most efficient flood fill algorithm. But I think it was at 15 by 21. Okay. And I'm just going to pop the seed here and give it a moment to do all those calculations, and it seems to be working. And the center tile is always empty. There's nowhere an obstacle could spawn that would cause them to get trapped. What about right there? Nope, you can come all the way around here. All right. And if we reduce that, it should go, oh, whoa, that was some lag. Before we finish, let's remove these print statements because these are actually the most inefficient part of our code at the moment, causing the most lag. And that'll speed up our flood fill algorithm. All right, well, that was cool and fun. I hope you enjoyed that. I hope it was easy enough to follow along. I know fancy algorithms like that take a little bit of time to wrap your head around. I'm hoping to get the opportunity to explain and code a few more algorithms like this. I enjoy doing it. I love playing with them. Until next time.